with part A, that's just a fairly routine problem, approximately 40%. So that's your probability of success. And in part A, you've got a number of trials is N, which is 20. And so here, X represents the number of seedlings that survive their first year. So you could potentially have 0, 1, all the way up to 20. And you want the probability that at least half of them survive. So we should go in with a binomial. 20, probability of success is 0.4. Probability that at least half of them survive, which means 10 or more. So this is where you're going to your calculator and then do your calculations. I'm going to do this one by e-activity only because it's there, it's available if you want to use it. I prefer not to, but if you want to use it. I find that if the e-activity stuffs up, people get all flustered and they don't know what to do in the middle of an assessment. So, because then if it's going to stuff up, inevitably it will be during an assessment. So, but it does allow you to set up this in a way where you can solve for that probability. So, whoops, in this case, the lower bound, let's go back to it, sorry. I don't know what happened there. No, it's died. Maybe not. All right, so X greater than or equal to 10, which means we start at 10 and we end up at 20. Number of trials is 20. Probability of success is 0.4. And then we just solve for P. And there it is, 0.24466. Now, I'm suggesting 5 you should get into the habit of putting all of your probabilities to 5 decimal places. I've said that on my videos. Unless there's lots of zeros. If there's lots of zeros in there, then add a few more. But if there's sufficient, 5 decimal places is the way to go. Definitely not 2 or 3. That's not enough. Okay, not enough refinement there. Okay, so the part B is the one where you've got to practice this idea, where you've got a different distribution now. We want to know how many, a new n value, it's not going to be 20, it'll be some n value. So I'm going to call it a different letter, y. We don't know what n is, but we still know that the probability of success is 0.4, so that hasn't changed, because that's in the original part to the question. So we want n such that the probability that X is greater than or equal to 5, so we want at least 5 surviving, and you're going to have more than, is greater than 0.5, is more than 50%. So this is where you would use the binomial find n, or guess and check on your calculator. Either way, it doesn't matter. And just overriding. So this time your probability of success, and if you ever, no, my calculator's still not liking me at the moment. So if you ever are unsure what those numbers should be, just put in help. Just press the help button and it'll tell you, to remind you. So it should be, if you're doing this properly, it should be the 0.4, then the 5, and then the 0.5. And if you call this up, you should get at 12, 0.561 something, and 11, the probability is 0.467. So 11's not quite enough. So you've got to plant 12 seedlings to be 50% sure that at least 5 will survive. That's what the question is asking there. It just, you stick with one and use that one all the time. It's better, unless you want the graph. So start with lower bound is 6, upper bound is 6, so they're both the same. Number of trials was 10 patients, and the probability of success was the 0.8. So if we set that up, we should get 0.08808. So at least 6, so that means 6 or more. So back here, your upper bound then goes from 6 to 10 now because we want at least 6 successful. So 6, 7, 8, 9, 10, and therefore 0.9672, which makes sense. Yeah, you'd hope there'd be a high chance of lots of operations being successful. Now, is successful for only the first 5 patients. What's different about this one?
First 5?
It's correct. It's the first 5, not any 5. So first 5 were successes, and then the second 5, not successes. So we've got to fix those probabilities. You cannot use the binomial for this. So you've done examples like this before. So it's those first 5, 0.8 times 0.8 times 0.8 times 0.8, so 5 of them. And that, and it's not comma, sorry, that's multiplied by 5 unsuccessful in a row as well. So if we work that out, I'm getting 0.0010, and probably a few more decimals would have been good there. And try the next one then. This is the focus of today's lesson, which is that same idea. We're going backwards to solve for n. I'll go through this in a minute. So that's our final solution. There's nothing different to those other ones that we've done in the past. So just before we move on to those practice questions, I just want to talk very quickly about what I left you to do on Friday, which was these ones. Well, not so much the first few. That we've practiced that binomial. If you followed my notes and listened to my videos formally and in succession, we've already covered this same kind of idea. So this was just more practice on that. But what I wanted to really make sure of is this type of problem where we can't use binomial, which we actually just did one previously. So as in part B, and also this type of problem where you actually are limited in where you can use the binomial or not. So I tried to be clear with my solutions there. So if you're not sure about that one, or if you haven't tried it, make sure you do. And the other thing I wanted to show you is the difference between when you can use binomial and when you can't. So this question here in particular, so you've got a scenario where I've tried to use the same question but showed you the variation. So this question, you've got 20 koalas, 20% of them have the disease. So 20% of that 20 only. So you're pulling koalas out of that group of 20. So as soon as you pull one out, your sample space changes because you're pulling one out and your probability changes. Because if you've pulled a koala out who's got glaucoma, then your probability will be different to if you pull one out that doesn't each time. So in this case, this is one of those ones where in one of the very first lessons we did on discrete random variables, you had to use counting to work out the probability because each trial is not independent. Once you pull out a koala, you don't return it back to the pool of 20. The next one is actually the same, but except there's 20,000 as opposed to 20. And the reason why I gave you this one is to show you that when you've got such a large number, it kind of makes not much difference. Exactly. So when you've got such a large number here, you can see how close those answers are in comparison to this one, where there was a bit of a difference, at least to the second decimal place. And so this is saying all the koalas in the wild. So it's not just this fixed 20 or this fixed 20,000, it's all of them. All the koalas in the wild. This is, I'm choosing 6 from all of them. This is where, well, if you choose one and then another, we're not changing the probability of the next one having the disease. And so this is when you can use binomial. So we talked about one of the conditions for the binomial distribution, and this came up in last year's WACE exam, and one of them was that the trials had to be independent. So that's when you can use it. Like I said, when you've got a large number here, there's hardly any difference between the two probabilities, but when it is a smaller number, you should be using counting to do that. So like I said, I wanted to highlight that. So if you haven't done that, it's an important document to do because it does cater for different sorts of questions that you could be asked. And I might consider putting in your exam. Okay? Including what we did today.